Today's section is 1.6 polygons, and we start off with a really long, probably a run-on sentence for those English people, but let's go through a lot of vocab terms that are underlined here. Polygons are closed figures formed by a finite means a set number of coplanar segments that are on the same plane, such that the sides that have a common endpoint are non-collinear, not straight lines, and each side intersects exactly two other sides only at their endpoints. And you read that and go, whoa, what does that mean? I think it's easier to show you examples than try to explain that a little bit more. So all of these are examples of polygons, these three objects right here. Yes, polygon, yes, polygon, yes, polygon. So again, you can see they're enclosed. They have all vertices, closed points, and then on the next slide, you're going to see examples that are not polygons. And then how do we name polygons? You could say this is polygon. You could say A, B, C. Again, it doesn't matter what order you go in, but you have to be continuous. So in this example right here, we are going to say polygon, we could say polygon E, F, G, A, B, C, D. So you just have to go in some continuous order and hit the vertices in order. You can't jump around. You cannot say polygon F, D, B, E. You cannot jump around like that. It just has to be continuous with whatever letter you start with. And then this example here, polygon, we could go E, D, C, B, A. So as long as you go in a continuous way. These are polygons. This slide right here shows the examples of non-examples. So again, this doesn't connect. They don't get to a common point. This one is a little bit rounded right here and a little extension right here. Polygons don't cross through the middle, so those are non-examples of polygon. Next concept we want to talk about is something concave or is something convex. So I'll read this. Any polygon whereby if the side segments are extended and that extension passes through the interior, then that is called concave. So again, people don't like to go inside the cave. So if I extend here, that goes inside the cave. So if you extend any of the lines and it passes through the inside, so I know this does not, this does, that goes inside, so in the cave. If I do the extension on this example right here, none of these will pass through the inside of the object. So this is convex. This is concave. It goes through the middle, through the cave. Concave, convex. Next one right here is how do we name polygons? So if we have a three-sided figure, obviously that's a triangle. Four-sided figure, quadrilateral. Five-side pentagon. So this is a way that we name polygons. Six-sided hexagon. So this is the way we name objects. Now I don't know exactly why that they skip 11, but they go to 12, dodecagon, and anything after 12. An example would be a 14agon. So a 14-sided figure would be called a 14agon. So taking a look here, this next definition concept is whether something is regular or irregular. And we will use this throughout the year. It'll come up in examples, so you need to know what is a regular object. Is a polygon, regular object, polygon, where all sides and interior angle measures are congruent. So these are all equal, and these angles, interior angles, are all equal. So again, all the sides are the same. So in this case, all these sides are the same. And interior angles are all the same. So that's what we mean by irregular objects. These examples are irregular. This right here does not equal that. This right here does not equal that. This side right here does not equal that. So sides and interior angles. So now let's classify these. Three different ways to classify. We want to use, well, first we want to name it. Name the polygon. Is it concave or convex, regular or irregular? Example A is a quadrilateral, convex, and irregular. Example B, nonagon, concave, and irregular. Next slide, we're going to get into some mathematics. This is a very challenging problem, multiple steps that go with it. So this example, a masonry company is contracted to lay 3 layers of decorative brick along the foundation, and they give you the perimeter of the foundation. So obviously, take a look, give it a try, see what you get. First thing I do is I find the perimeter, so I add all of those numbers up, and we get 216 feet. 216 feet. Where we run into problems, though, folks, is they give you feet here, and they give you inches here. So you have to make a conversion. We're going to convert these feet into inches. So if you've never done a conversion, we want feet down here to inches up here. Feet cancel out with your units. There's 12 inches in 1 foot. So in this example, you would multiply across the top. There's just 1 in the bottom, so you just have to multiply. So we have 2,592 total inches. 1 brick covers 8 inches. So you're going to divide that number to give you an idea of how many bricks that we're going to need. That's 324 bricks. But if you remember, it said up top they want 3 layers. So we have to multiply this by 3, get a total of 972 total bricks for this problem. Okay, so the next problem here is going to take us to a sketch. So you could sketch this. Take a look and see this is what we end up with on the sketch. Get this out of here. Give us some room to work. So what we want to do here is we want to find the perimeter and area of this object. So a couple things. So down here we can count. We want to find the perimeter. So that means we have to find what is the outside length of all of these. These one you can count. 1, 2, 3, 4, 5. So this side is 6 units in length. Those ones you can count because they're straight and they're right on the lines. This one you can count. 1, 2, 3, 4, 5. So we know that this is 5 units and this is 6 units. But now when you get to this example right here, EA, you can't just count. We actually have to use the distance formula. So I don't know if you remember the distance formula, but again, this is where that comes into play. x2 minus x1, quantity squared, plus y2 minus y1, that quantity squared. Let's plug in some values. We're going to do AE. So we're going to do AE. So hopefully you remember how to do this from the other day, and if not, so here's E right here. Here's A up here. So what I'm going to do is I'm going to go negative 3 minus 0, that quantity squared, and then I'm going to go 1 minus 4, that quantity squared. So over here, negative 3 minus 0 is negative 3, so we're still under the square root. Negative 3 squared, plus over here, negative 3 squared. So negative 3 squared is 9. Negative 3 squared is 9. 9 plus 9 is 18, so the square root of 18. Yeah, in this case, I'd like to have a decimal, so we're going to get about 4.24. So we know that this is 4.24, so I'm going to write that in. Now we want to find AB. So we have to find AB, and we have to find BC. So again, yeah, we're going to have to do 3 distance formulas in this problem. So again, we go up here, here's A, here's B right here. So again, we can go 0 minus 4 quantity squared plus 4 minus 0 quantity squared. So 0 minus 4, negative 4 squared, and 4 squared. So both of these cases, we're going to get 16 plus 16. So that's the square root of 32. Yes, we want a decimal for that as well. And that is going to be about 5.66. So now we got 2 of those done. Let's do the last one here is going to be BC. So we have BC. Again, distance formula here for BC. B is 4, 0. C is 3, negative 4. So we can go 4 minus 3 quantity squared. And we can go 0 plus 4 quantity squared. Whoops. That was supposed to be parentheses squared. So this example right here, 4 minus 3, 1 squared, and 4 squared. So in this example right here, we have square root of 1 plus 16, so that is a square root of 17, and that is about 4.12. So let's write that one in. So we have 4.12 here, 5.66 here. You add up all of those perimeters, we end up with a perimeter about 25.02. 25.02. Okay, I'm going to erase all that since you all have it recorded now. And now we want to talk about area. We want to talk about finding the area. See if I can erase this real quick. Great. All right, so if I ask you to find the area of this object, now that's on the inside, what you want to do is you want to break this object down into objects you can work with. So I'm going to take this right here. It kind of looks square-ish, but it's a rectangle. And then we have a triangle up here, and then we have a triangle here. So the first thing I'm going to do is, this is 6. We already got that from the last one. This is 5. So we have 5 times 6. This section is 30 units squared. Up here we have a triangle. So area of this bigger triangle, remember, is 1/2 base times height. So base times height. Base is on the bottom here. Bottom, you count this. 1, 2, 3, 4, 5. So that's 6. Your height, yeah, you can count these. This is 1, 2, 3. So 3. 1/2 of 6 times 3 is going to give us 9. So we know that the area of that triangle is 9. The area of the other triangle is the same equation. This base is 1, 2, 3, 4, 5. So 1/2 of 5, and your height is 1. So 1/2 of 5 is 2.5. So we have 2.5, we have 3, and we have 30. All of those add up to the 41.5 units squared. So here's your area. So that gives us a perimeter in the previous group, and that just gives us an area right there. One last equation here, folks. They want you to find the width of a rectangle that's 5 less than twice the length. So that's using some algebra stuff. So first thing you want to do is you want to set up an example. So there you go right there. So we have the width. So width is 2 times L minus 5. So if you remember how to set this up, it says the perimeter is 80 centimeters. So you have to add up all 4 of these. Add up all 4 of these. And in this case, they just double it. 2 times that, 2 times that. You can see the algebra that goes into it. And you can find that the length ends up being 15. You plug it in to find the width of 25. So the original problem says find the length of each side. So we have 15, 15, 25, and 25. Great job on the notes. Thank you.